So we once again started learning the basic addition, and two numbers. I gave an example how to add two numbers, and essentially what we need in that exercise is the basic fundamental thing I must know is the sum of two digits. So here we have this sum that we did last time, and we saw that how I should know 1 plus 5 or 6 plus 3 or 0 plus 7 or 7 plus 8, and then there is a carry, there is a sum, carry and sum. So essentially if you think it is as a device, what we are giving is we are giving two numbers A and B, and we are taking two outputs, sum and carry. So in all of these kind of equations that is written, these are the two input numbers, these are the two input numbers, and these are the two outputs. One output you can call carry, another output you can call sum. Same thing happens in the binary number addition also. The benefit is that we have only two digits, two symbols, and therefore the things are less in number, simpler. So let me do a addition of two numbers written in binary system. So let us take two numbers in binary system. So I have two numbers, let's say 1 0 0 1 1 1 0 1, like that, and then the next number could be 1 here, 0 here, 0 here, 1 here, 0 here, 1 here, 1 here, 1 here, like that, and we have to add. So what do I need? 1 plus 0. So I should know that 1 plus 0 is 1, and if I write 1, I also write 0 here. So this is carry digit and this is that sum digit. So 1 plus 1 gives me sum that I write here, and carry I write here. Then 0 plus 0. So I should know that 0 plus 0 is 0. So sum is 0 and carry is 0. And that sum is to be added in this. So 0 plus 1. So 0 plus 1 is also 0 1. So sum is 1 and carry is 0. So 0 plus 1 will be 1 and 1 plus 0 will be 1. So this will be 1 here. Then comes 1 plus 1. Now what is 1 plus 1? So 1 plus 1. So the number next to 1 in our counting, we have one digit numbers, exhausted, then two digit number, exhausted, then three digit number, and so on. So if I add 1 to this 1, I get the next number, consecutive number, which is 1 and 0. So that 0 is the sum and 1 is the carry. So I put the sum here and carry here. And then 1 plus 1 is again 1 0, and 0 is the sum and 1 is the carry. So this 1 plus 1 is 0. So I have to remember that sum is 0, and that sum is to be added here, 0 plus 0, and that is 0, and that carry still remains. So that carry goes here, and then 1 plus 0 is 1, and that 1 plus 1 is 1 0. So this 0 goes here, 1 goes here, 1 plus 0 is 1, 1 plus 1 is 0 here and 1 here. And now I have 1 plus 1 and plus 1. Okay, so 1 plus 1 and plus 1. So 1 plus 1 is 1 0. This 1 and this 0. The sum is to be added here, and carry I have to remember. So that sum is added here, and then that gives me 1 here, and that carry goes here. There's nothing here, 0 0. So that is 1. That is how we sum the numbers. Similar procedure as we did in decimals. So the basic things I must know for this addition is addition of these two digits. So if I write it as a device, then my inputs are here A and B. Let's call it A and B. And I have two outputs which I can call C and D. C and D, and then this is some kind of a circuit, digital circuit, and then the circuit should be such that if I write A here, B here, and S here, and or let me write C here and S here. Okay. So if this is 0 0, if this is 0 0, I should get 0 0, 0 carry and 0 sum. So it should be 0 and 0. If it is 0 1, then I should get sum as 1 and carry as 0. If this is 1 and this is 0, once again I should get the same thing, and if this is 1 and this is 1, then carry should be 1 and sum should be 0. So this is the input output, that is our requirement. My circuit should do this. This circuit should do this. If I take this A as 1 and B as 1, I must get the output C carry as 1 and the output D as 0. And similarly for all combinations. Since there are only 2 inputs, so I have 4 combinations. So when you exhaust all the combinations of input and tell what should be the output corresponding to these inputs, that table is known as truth table. This is known as truth table. And our circuit will take these inputs, that means voltages we will provide, low and high. We have to predefine, normally say 0 to 0.8 volt or 0 to 1 volt is low. So anything, if I apply 0 volt here, 0.5 volt here, that is low and that will be treated as 0. And anything if I apply here which is predefined more than 2 volts, that I can define how much is that. So if it is high, if it is that high voltage more than 2 volt, then that is 1, and similarly for B. So this is the kind of circuit which we call digital circuit, which takes only digital inputs. It takes voltages, it takes only voltages, but those voltages I see it as digital, either low or high. I do not distinguish between 1.7 and 1.8. So for us it is digital, 0 or 1. So this is the kind of circuit. Now how to design such circuits? How to design such circuits in which the input is given as voltages, and depending on whether it is high or it is low, desired output is achieved. This is, by the way, this is this truth table, this kind of combination, this is also known as half adder. Why half adder? Because here you had seen I had this 1 plus 1 plus 1. So I had to do some mental calculation. 1 plus 1 will give me 1 carry and then 0 sum, and then I have to remember that okay, the carry is still there and sum is to be added in the sum, and so on. So if we can put 3 numbers together as input and then ask what is the final sum and what is the final carry. So that means I will have a circuit in which 3 inputs will go, A, B and C. A, B and C, like here 1, 1, 1, here 1, 0, 1, 1, 0, 1, 1, 1, 0. So there are 3 inputs, and then I need the final sum and final carry. I don't want to remember in between what happened and then carry in my mind also. So if I have this kind of circuit designed and then I say that okay, I need the final carry and the final sum, you can make your truth table. Okay, you can make this kind of table. This time you have okay, let me not call it C, C is for carry, let me call it D or X, Y, Z. Let me call it X, Y, Z. No confusion, X, Y and Z. So you can make a table, X, Y and Z, and then carry and the sum, and then you can put numbers here, 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 what should be the carry, what should be the sum. How many rows will be there? How many rows will be there? There are 3 inputs, Each input can be 0 or 1. So there are all those combinations are to be written. All those combinations are to be exhausted. 0, 0, 1, 0, 0, 0. Everywhere you have to make so 8 rows, and for each row you know how much is C and how much is S, and that kind of truth table, that kind of circuit which can do this, that is known as full adder. So any digital circuit which takes digital input and gives digital output, that is digital circuit. It takes digital input means it's an amplifier, it's a transistor, or it's some electronic circuit, combination of diodes, transistors or resistances. It's a circuit, electronic circuit. An electronic circuit only takes voltages and currents, okay, and it gives output as voltages or currents. But then the design is such that if the voltage is in this range, and if I call it 0, and if the voltage is in that range, I call it 1, and similarly for output and for input, then I should get this truth table implemented. So that is the digital circuit. It takes digital inputs and it gives digital outputs. Could be one output, could be more output, could be one input, could be two input, could be three input, and so on. Okay. All right. Now, to design such a circuit, the basic blocks with which you design complicated circuits are called logic gates. So logic gates. These are themselves digital circuits, and there are several of them I will describe, and these are taken as the basic blocks. So you have one single unit, one integrated circuit. You go in the market and say this logic gate and you get that. So the whole circuit is inside, and then use those gates and combine them in appropriate fashion to design the circuit which gives you desired outputs at desired inputs, right? So some of them which are very basic and which I will describe. The first one is, let's talk of this NOT gate. This is called NOT gate. And what is this? It's very simple. It takes one input and it gives one output. So this is NOT gate, and NOT gate takes one input, just one input, and then it gives one output. A, let us call it A, and let's call it Y. So if A is 1, a truth table is very simple. If A is 1, then Y is 0, and if A is 0, then Y is 1. Finish. This is the truth table for NOT gate. So if this is 1, this should be 0. If this is 0, this should be 1. That kind of circuit is known as NOT gate. And you must remember, we have already discussed this kind of circuit. And it's nothing but a transistor in switch mode. Okay, a transistor in switch mode. So if you have a transistor, if you take NPN transistor as we had been doing it, you have that load resistance or collector resistance, and then you put your biasing here, you put some resistances, some capacitances, all those things I am not showing. And then here is that input, right? So you can put a resistance here, you can put a resistance here, and then this is the input point. So essentially this is it, it's like this, and that's So this is that point A, and you can take your output from here. This is the point Y. Okay, so if you operate it as a switch, that means this voltage is given high. Suppose you give 5 volt here, and then this base emitter junction is forward biased, and it goes, and this is sufficient to drive the transistor in saturation mode. Okay, you have cutoff mode, you have saturation mode, in between you have that active mode, linear region. Right? So be in saturation mode or in cutoff mode. So if the voltage is given here, if sufficient voltage is given here, so that you have driven the transistor in saturation mode, then the maximum possible current can go in that configuration, and then you have a current from here, and once you have current from here, then you have drop, you have potential drop here, okay, and therefore this potential is low, right? In collector, current goes like this. This is NPN, remember. So it goes like this, and so this is high voltage, but then you have drop here, and this becomes low voltage. So if you put high here, if A is high, Y is low. Okay, you apply a voltage, a high voltage. High voltage means not 1000 volt. High voltage means in our case is just 3 volts, 4 volts, 5 volts, which drives this into saturation mode. So that there is a current from here, there is a potential drop, and this becomes quite low. And if you give this low, you don't put a battery, you give 0 voltage here, then no current goes, it in cutoff region. And since no current goes anywhere, no current goes here, so the potential here and potential here is same, and this potential is high, so this potential also becomes high. So this transistor, single transistor itself is a NOT gate. So you give one input, you get one output. If the input is 1, output is 0, and if input is 0, output is 1. And there is a symbol for it. Okay, symbol for NOT gate, and that symbol is, you put a triangle and put a line here, put a small circle here, and then a line here, and this is the input, this side is the input side, and this side is the output side. So this circle actually denotes NOT operation. So this is the symbol for NOT gate. So this is one, simplest one. Then next is, let's take AND gate. So the next one, let us take AND gate. It is called AND gate. This AND tells that if your all inputs are high, if you have 2 inputs, the first input should be high and second input should also be high. So if both the inputs are high, then the output is high, and if any one of them goes to low, or both of them go to low, then the output is low. That is why the name AND. So that means if I draw the truth table, if it is 2 input and 1 output, the basic AND gate will have this. You can have more inputs, but the basic AND gate will have 2 inputs and 1 output. So if this is 0, this is 0, this is also 0, right? And then if this is 0, this is 1, still this is 0, because A and B both should be high to give you this high value of Y. So 1 and 0, that should be 0, and 1 and 1, that is equal to 1. So if you have a circuit of this kind, that circuit will be called AND circuit. right? Both of them should be high, then only the output is high, otherwise it is not. So it's not our binary addition, 1 plus 1 is 1 here. So that and it should not be taken as addition or this 2 and 3 makes 5, it's not like that. Now this kind of thing you can think without any semiconductors or anything, like a switch. So you can have 2 switches. It's just to conceive the idea what is AND. You can have 2 switches, and this can be treated as input, and then you have a lamp out here. So this is your output, this is a lamp, and this is our output, and then you have a appropriate battery or power source. Okay, so you can treat this as A, this as B, and this is Y. Lamp on, Y is equal to 1, and lamp off, Y is equal to 0. So that's the output. And input, switch S1. So any switch, if it is closed, closed means connected. So if the switch is closed, that we will call 1. This is your input, A or B, and if the switch is open, as it is shown in this figure, switch is open, so that we will call 0. So if you take this as the meaning of 1 and 0, then you can see that if A is 0 and B is 0, if A is 0 and B is 0, switch is open, both switches are open, and then the lamp is not glowing, and you say that Y is equal to 0. And if one of the switch is closed, other switch is open, so A is 1 and B is 0, so A is 1 and B is 0. So that case also there is no current in the circuit, the lamp is off, and therefore Y is equal to 0. If this is open and that is closed, then also the same story. And if both the switches are closed, so that this A is 1 and B is 1, then it glows. And if it glows, if it is on, then we say that Y is 1. So 1 and 1 is 1. So this is the meaning of this AND. You can make this AND digital circuit using PN junction diodes. Let's see how. So let me take 2 diodes, one diode here, PN junction, this is P side, this is N side, you remember that. Then another diode here, and join this together and put a resistance, and then a battery cell here, could be 2 volts, 3 volts, and this is our ground, this is our ground. And let these 2 be the input points A and B, and let this be the output point Y, and see if this can do that AND operation. What is that AND operation? The AND operation is if A is 0, B is 0, Y is 0. Then if A is 0, B is 1, then Y is 0. If this is 1, this is 0, then this is 0. And if this is 1, this is 1, then this is 1. That is the AND operation. So what happens if this A is 0 and this B is 0? That means this is given 0 volts, this is given 0 volts. I am connecting this to the ground, I am connecting this to the ground. Remember this kind of symbol? It means that this is connected to this line here, and this is also connected to that same line here. So in this case, both the diodes are forward biased. you have a higher voltage here and a lower voltage here, so it is forward biased, and therefore you have current through this diode. The current goes like this and then it comes back and goes into the battery. The current goes like this and comes back and goes into the battery. And since the current is going, it is forward biased, the drop here on this PN junction is very small, 0.2 volts, 0.3 volts, 0.5 volts, not more than that, 0.6 volts maximum. So if this is 0, this will only be a small voltage here, and for digital operations that is same as 0, low. So this is low voltage, and therefore Y is 0, Y is 0. And then what happens if A is 0 and B is 1? A is 0 means A remains grounded, but now B is at 5 volts. This B is at 5 volts. Let us say 5 volts. So if we have put 5 volts here, that means we have put a battery, another battery here, and that battery is connected to this negative here, and this is a plus 5 going that. So what happens? This becomes reverse bias. You have put full 5 volts here. So no current through this. No current through this. But doesn't matter. This is still grounded. A is 0. This is still grounded. And therefore, this is higher voltage, this is lower voltage, this is forward biased, and therefore the current will still be there. And once the current is there, once again the same story, if this is 0, then there is only a small voltage which is 0, and here it is 5 volt, let it be 5 volt, this is no current is going, so it is just possible, this side is 5 and this point is very small volt, so that is fine. So this is low, so this is a low. And similarly, if A is 1 and B is 0, then this will be 0. We are only changing the these two, swapping these two, put 5 volt here, put 0 volt here. Then this will be reversed bias, no current from here, and the current will be only from here. What happens if A is 1 and B is 1? This one, A is 1 and B is 1. So I am giving 5 volt to A and 5 volt to B. Now both the diodes are reversed bias, no current going from here, no current going from here, and therefore no current going from here, Kirchhoff's junction rule, no current going from here. So whatever is this voltage, that same will be this voltage, and therefore this will be high, and hence you have 1, 1 and 1. So this is how this AND can be implemented using this diodes. I can also do this using transistors. We had shown how that switches can be used to light that lamp and that equivalence of that AND circuit, and transistor can be used as a switch. So that same switch circuit I can put 2 transistors and then make this AND circuit using those. So next time I will show that, and then we will talk about several other gates and their circuits.